Welcome to another Science on Saturday. We are so thrilled to have you. This is the penultimate lecture, I love that word, of the 2023 Science on Saturday series. So today and then next Saturday, and then we will sadly say goodbye until next year. I know, right? I like these. This is a highlight of my week. So for those of you who may be here for the first time, welcome back. We missed you. For those of you, I see so many familiar faces. You've had me say this to you every time. I'll keep on saying I still miss you. So there are a whole bunch of people online, but of course, we were just chatting. Masks continue to be optional. We keep on monitoring the health conditions here. If something were to change in the next week, then we would switch to masks are mandatory, but they're certainly optional right now. Normally, I say hold all questions until after the presentation, but I guess we have a different type of presentation. Can you, well, we'll get there in a second. I want to make sure Harry, his mic is up high enough. And for the Zoom folks, use the raise hand or put it in the chat, and I'll grab as many of them as I can. So Dr. Battaglia is here for today's, and then next week, we're going to have a colleague of his from the same facility in conversation with a fashion designer who has designed a part of a collection based upon plasmas and fusion and the shape of tokamaks. And so we're going to have a conversation next week about art, science, fashion, the intersection, how science inspires fashion. And I think what'll be very interesting as well is to find out how, if any way, that these sort of collaborations inspire science. But with that, it is my pleasure to welcome to the Science on Saturday stage, Dr. Devon Battaglia, who's the head of physics at operations for the SPARC Tokamak at Commonwealth Fusion Systems. Before he was there, he was at this place that's called the Princeton Plasma Physics Laboratory for many, many years, where you see he led physics operations for the National Spherical Torus Experiment upgrade. He also is a great singer and dancer, the star of one of our many holiday skits. And he's participated, if you do fusion, then you've participated in the operation of a variety of tokamaks around the world and served on national and international committees. And with that, would you please welcome him to the Science on Saturday stage?
Thank you.
The floor is yours.
Oh, thanks.
I do have 3 questions, but
that's right.
And make sure his mic is good. Let me know if you can hear him. So first question, please tell us, at what point in your, from here to here, did you first start getting interested in science?
Thanks, Andrew. And thank you everyone for coming out on a very rainy, cold day. It's great to be back in the auditorium where I have a lot of really nice, fond memories. So for me, I'm a child of the 80s, and it was the shuttle program. Being very interested at an early age, not in the astronauts and the missions, but also in just this really cool thing that could go up. And recently, my family went to the Kennedy Space Center, and I will admit that I was a grown, sobbing man, and many times looking at many of the things there, not only because it was like seeing my heroes of my childhood, but also because of the parallels to fusion development and the challenges of pushing on science and technology, and then seeing their success got me excited for the success that's going to come in fusion development.
Excellent. Thank you. How about now a teacher? Could be anywhere from preschool to graduate school.
I'm going to break the rules a little bit. I'm going to go beyond.
No, he breaks every rule.
I'm going to go beyond graduate school. So PPPL, one of the missions is education, right? And this is part of that. For me, as an early career scientist, starting off here, there's so many terrific mentors. Not only taught me how to be a good scientist, but how to be the right kind of scientist, one that cares about not only what they work on, but who they're working for, which is society. And so I sort of tip my hat to just the organization of education that's here at PPPL.
Thank you. I appreciate that very much. Some of them are in the audience right now. So, and then the last question. a hobby or something you do when you're not working?
Well, you already kind of revealed that I am an amateur at performance. And I did that a lot in college. I played trombone, I sang, I did musical theater, I danced. But as you go through your career, you start a family, you have a house that always needs some kind of work to be done. That has fallen by the wayside. But now performing with my kids is really sort of my hobby. So dancing wildly to Disney music, playing trombone with my son. So things like that are my hobbies now.
Do you remember, and if you do, could you share with the audience your hit song, the title of your hit song at the last PPL?
What happens in the holiday skit stays in the holiday skit.
He's a smart man. So I think, hold on for a second. Harry, what do we need to do? Get out of this one. And then Harry, can you share his slides from up there? Highfield Tokamak. Oops. Highfield Tokamak is the fastest and surest. Nope. Which happens first? Fusion or there we go. There it is. Highfield Tokamaks, the fastest and surest way to a fusion energy power plant. Dr. Devon Battaglia, the floor is yours.
Thank you. Thank you, Andrew. I've actually, this is the first Science on Saturday that I've attended. I'm, sorry to say that, but one of the things that is legendary about the Science on Saturday that Andrew and others would always brag about is how engaged and educated the audience is. So I'm not going to say that I'm going to put that to the test with this next slide, but sort of give an opportunity to display it. So in the category of things that are good to know for this talk, the $200 question, and then in sense of if you recognize this from Jeopardy, your responses should be in the form of a question. Please, no buzzers, but raise your hand if you can answer a response to it is a reaction where atomic nuclei combine. I saw a very quick buzzer in right here. Thank you, sir. That's right. Thank you very much. The $200 is yours. What is fusion? So all the heat and light that we feel from the sun is due to the process of fusion, where light atomic nuclei are combining to form heavier nuclei, and energy comes out of that. Now, the thing, if you ever want to just sort of blow your mind, is to think about that pretty much everything that is in our world that isn't hydrogen came from the center of a star. Oxygen, nitrogen, carbon were all formed through the process of fusion inside of a star. We are stardust. And this is how, thanks to fusion, we feel all the heat and light from the sun. So we're now going to go down into the $1,000 question of good things to know for this presentation. This one is probably the most challenging. They are isotopes of hydrogen, all the way in the back, sir. Yes, thank you. Thank you very much. Yes, what is deuterium and tritium? Yes. So I'm gonna put a little context to that response. So an isotope of any atom has the same number of protons in the center of it, the nuclei, but could have different number of neutrons. So in the case of the element helium, the traditional form that we're used to has one proton and an electron zipping around on the outside. Its scientific name is protium, but we typically just say that's hydrogen. There are isotopes of hydrogen, so they have neutrons that are added to the center of the atom. So when you add one neutron, you end up with an isotope that's now termed deuterium. And if you add two neutrons, you have an isotope tritium. Now you'll notice as you walk out of here by the PPPL plasma hutch, they will sell you a proton for $10, but the neutron is free of charge. It's a good dad joke. So I introduced this concept of isotopes because it's important as we look to the remainder of this talk on fusion. This particular reaction of fusing deuterium and tritium is a process that releases energy. And the reaction is shown here where one deuterium nuclei is brought together with a tritium nuclei, and the results are a helium nuclei and a neutron, and both the helium and neutron have gained energy from that reaction. So this is a potential energy source that we can use on Earth if we can harness the process of fusing deuterium and tritium. So why deuterium and tritium? Why these isotopes? Well, these two isotopes of hydrogen, very light atoms, fuse at the coldest temperatures. So this is a plot of, on the vertical axis is a number that means how easily these atoms are going to fuse together. And on the bottom axis, the horizontal axis, the x-axis, is how much energy it typically takes to get that process to happen. And they're in a bit of scientific notation. So up at the top, I noted where 100 million degrees Kelvin is in that energy. So these are very, very hot temperatures that get the fusion process to happen. And a lot of times people maybe envision we're bringing two nuclei together and they fuse, but actually they're trying many, many times. You have to have many, many collisions between these nuclei before statistically it's going to happen. So we need a system at very, very high temperatures where the nuclei have many opportunities to interact for the fusion process to occur. And this can happen inside of a star because it's very large, gravity's keeping things together. They have many, many opportunities to collide at the temperatures needed for fusion. Okay, thanks. We're going to go on to our $600 question. It is the fourth state of matter. Sir, I saw you in the maroon there at the aisle. Quick. What is plasma? We are at the plasma physics lab, the Princeton Plasma Physics Lab. Thank you very much. Good answer. And it is the fourth state of matter. So the ones that are kind of the states of matter we interact with on a day-to-day basis, solids. And if you put energy into a solid, it could melt, turn into liquid. You put energy into the liquid, it would evaporate, turn into gas. If you put energy into a gas, you can turn it into a plasma. Any gas that's glowing, you can think plasma. So flame, neon lights. So the key property of plasma is that the electrons have been pulled off of the positive nuclei that they normally were orbiting around, and you end up with a soup or a mix of charged particles. So the reason that I brought up this new concept of plasma is when you get things to the temperatures that you need for fusion, a gas at the temperature for fusion, it is going to be a plasma because you have put a lot of energy into that gas. Now, one of the neat things about plasmas is because they are a sea of charged particles, electrons and protons or nuclei, they can follow the track that you make out of a magnetic field. So in the top where I have a picture that says no magnetic field, if you had a gas or plasma and the particles inside of it would be like bumper cars. They would move in every direction. They would bounce off each other, but they'd bounce off the walls too. And they would lose energy to the walls as they bounced around. And if you want to have something at 100 million degrees Kelvin, and you want to have room temperature walls, it's going to be very hard to have that temperature difference because everything that's hot is going to transfer its energy to those very cold walls. By placing a magnetic field through your pipe, as it's shown in this picture, the charged particles, instead, it's like putting down railroad tracks. The particles follow those railroad tracks. They stay right on that magnetic field. And that allows you to maintain a very high temperature gas or plasma and a relatively cold wall and have that temperature differential. So the neat thing is that you can make a magnetic bottle for a high temperature plasma. So we get to our fourth question. It is a donut filled with super hot plasma. All the way in the back, yes, ma'am. What is a tokamak? Thank you for that answer. What is a tokamak? So I'm going to stay on this slide for a little bit because not only is the talk about a tokamak, but it is something that has a lot of parts that we should talk through. So The first is there are some blue rings that are making the shape of the donut. It's a cutaway here. And if you were to run a current through each of those blue coils, you would make a magnetic field track that went around your donut. So this is making the track for your super hot plasma. And you make that magnetic field by running a current, electric current, through the blue coils. Now, one thing that was discovered early on when making these magnetic bottles was that if you made it just with that track going around the donut, the plasma had a tendency to lose its energy towards the outside. And an analogy that I use sometimes for this, it's not correct from a physics standpoint, but at least gives the right picture of NASCAR race cars moving really fast around a track. If they spin out towards the outside. So something else was needed to keep the energy in the plasma from not being lost to the outside. And what was realized early on in laboratories like here at PPPL was that a twist was needed to the magnetic field, something that would allow the magnetic field not only to go around the donut, but to also go over the top and through the center. How a tokamak achieves that is actually running a current through the plasma, because the plasma is a soup of charged particles. You can run current through it just as if it was a metal. And if you run a current through the plasma, that's the jelly of your donut, it creates its own magnetic field. So that's shown with the green arrow running around the donut. And then there are other green arrows that are going through the center and around to show the magnetic field that's producing the twist. So the important thing is, if you look at the black line, that black line is sometimes on the outside of the plasma, sometimes on the inside. This magnetic field has a twist, like a barber pole, as it goes around the tokamak, and that creates the twisty magnetic field. And there are other ways to create twisty magnetic fields, but the tokamak is special in that it achieves it by driving a current through the plasma. The last bits are, there are coils that are on the outside of the tokamak that are going around the donut hole. They're in gray. And that's because this super hot plasma has a tendency to bond to expand like a tire, like a puffed up balloon. And also you want to keep it levitated inside your donut. And so these coils are used to shape the plasma, to give it the right shape that you want and to keep it where you want it. And finally, there's an inner poloidal field coil that runs through the center. And those could be used to treat the tokamak like a transformer. By changing the current in those coils, that actually will drive the current that you need to create that magnetic field. So I know I spent a lot of time on that slide. For the Science on Saturday crowd, I knew you could handle it. But if you want to take anything away, it's a magnetic bottle for a super hot plasma. And tokamaks have been developed for over 50 years, including right here at this laboratory, but really it's been a worldwide effort. So I show some of the progress in fusion power over the years, just to say that there is a rich, highly technical basis that has been developed by scientists and engineers that now exists in the world, thanks to investment in fusion research in the public sector. So I wanted to revisit my title, High Field Tokamaks, the fastest and surest way to a fusion energy power plant. And my hope is that this introductory, at least you're thinking, okay, I know what a tokamak is, and I know what fusion energy is. So the next part of the talk is to look at how do you take the process that we talked about in deuterium and tritium fusion and have that be a source that you would use in a power plant. So we're going to put my PowerPoint drawing skills on full display here to give at least a brief concept of the process that you would see in a fusion energy power plant. So the pink area is some plasma. It could be in a tokamak, but it is a confined plasma. And I have put in deuterium, which is the green and red dot, and tritium, which is the two green and red dots showing fusion, producing a helium atom, and also a neutron. Now the helium atom has 2 protons in it, and it is charged. So if you have a magnetic bottle, it stays trapped in that magnetic bottle, just like the deuterium and tritium were. And the energy that gets to that helium atom from the fusion process through those yellow arrows showing it can collide with other fuel, deuterium and tritium, and give it its energy. So some of the energy from the fusion stays in the plasma, keeps the plasma hot. But the neutron, free of charge, it does not stay confined in the magnetic bottle, and it comes zipping out. And so this is the heart of any kind of power plant. And for one, you're fueling your plasma with deuterium, so one of the fuels that you needed for deuterium-tritium fusion, and the exhaust coming out of your plasma is helium. The critical component in any power plant design is that there's going to be a blanket. It could be liquid, it could be solid, it's surrounding your plasma. So I haven't shown it around the plasma here, but it is something that is absorbing the energy and the neutron that's coming from the plasma with the fusion reactions. And if that blanket contains lithium, which is a very abundant minerals on Earth, the neutron can interact with the lithium and create tritium and helium. And the key thing here is that tritium is one of your fuels. And tritium is a rare fuel, so something that we would need to be able to produce at a power plant in order to keep the fuel cycle going. So at this point, what I've shown here is we have deuterium and lithium as our fuels. We have put in a little bit of energy to keep the plasma at the temperatures that we need. And we're getting out helium as a byproduct. And also the blanket is getting really hot. The blanket is getting hot from the energy coming off the plasma, but also the neutrons are embedding themselves in this blanket and depositing their energy from the fusion process. So the last thing that you do is you hook your hot blanket up to a heat exchange, and you boil water, and you make steam, and you turn a turbine, and you put that power on the grid. So a power plant, in essence, is deuterium, lithium, and energy going in, and helium and electricity coming out. And one of the wonderful things about fusion is you don't need much deuterium and lithium at all. You need kilograms of this type of material to run power plants for years. And so it is often viewed as a limitless energy source. I do remember fondly one time Andrew Zwicker talking about that, to bring your children to work day, and a child raising their hand and saying, it can't last forever. And Andrew said, well, it could last for a very, very long time. So the last thing that I wanted to sort of dial back is that's how a power plant would work. However, in the laboratory, including here at PPPL, we are very focused on the plasma itself, the heart of the power plant. And so there is a ratio that is often used, and it shows up in the news, and so I wanted to bring it up, of capital Q. And capital Q is describing the ratio of the fusion power that's being produced inside the plasma and the heating power that is going into the plasma to maintain the temperatures that you need for fusion. And so if that Q is 0, that means no fusion power or very little fusion power is coming out. If Q is very large, hundreds, thousands, it means that you're putting just a little bit of energy in and you're getting a lot of energy out. So it's hard to boil it down to an exact number, but power plants would need in the range of capital Q to 220 to 100. And it really depends on the efficiencies that are built around your plasma. And also for a useful power plant, the fusion power that is coming out of your plasma would be in the range of 500 to 1,000 megajoules of energy. So Q has been in the news. Hopefully this has come across your news feed over the last year, because it's been very exciting progress in the development of fusion energy. So one of them is the National Ignition Facility in Livermore, California, just a few months ago, the end of 2022, demonstrated a laboratory controlled fusion experiment where the Q was 1.5, or 2 megajoules went into the small pellet inside of a chamber called a holram, and 3 megajoules of fusion energy was created in that reaction. And I showed there that picture of that little pellet against the human eye. This is a very small pellet, and this process is driven by very powerful lasers. The second example here is from a bit earlier in the year, almost a year ago now, where this is at the Joint European Torus. It's in Cullum, UK. And this experiment it's a tokamak, uses magnetic fields to confine a super hot plasma. And in this demonstration, close to 180 megajoules were provided to the plasma to get it to fusion conditions. But it produced significant amount of, the record-breaking amount of fusion energy, 59 megajoules. But that Q was lower than what was shown in NIF. So you have sort of two examples, an example of Q breaking records and an example of fusion energy output breaking records. So if we are going to move from the experience like JET, where JET had a Q that was not at 20 or higher than what we would need for a fusion power plant, how would we do that? So if there's one plot that I hope you come away with and say, I remember that talk, it's this plot. And it's a model to give a rough idea of how you would achieve the Qs that you would need for a power plant. And the largest scalings are with the size of the tokamak and the magnetic field strength of the tokamak. So on this plot, on the green dot is where JET would fall in both magnetic field strength and tokamak size. So the tokamak size is being measured from the center of the donut hole to the center of the jelly of the plasma inside of it. And the magnetic field strength is how strong is that magnetic field track going around the donut. And in order to get to the Qs that you would need for a power plant, we either need to go up, which is bigger, or we need to go to the right, which is stronger magnetic field, or do a combination of both. So I hope now that we're at the point that we've talked about tokamaks and the application towards fusion energy power plants. And the next part of the talk will talk specifically about high field or high magnetic field. So last question of our Jeopardy challenge. It is a material with no electrical resistance. Yes, thank you over here. What is a superconductor? Thank you very much. You move on to double Jeopardy. So so in order to make our magnetic bottle, we need to create strong magnetic fields. And the way this is done is with electromagnets in tokamaks. So the strong magnetic field is created by running very large electrical currents through coils. Now, even if you use the lowest resistivity metal that we have, which is copper, it will heat up due to its resistivity. And we use resistive heating on a day-to-day basis. If you make some toast, it's using electricity to make the elements warm through the concept of their resistance. Superconductors are very special materials. They have no resistance. So you can run current through them and they're not getting hot. They're not losing energy. And the reason this is important for a fusion energy power plant is in order to maintain your magnetic bottle for a very long time at very high strength, if you're losing energy to heat, your power plant becomes less efficient. And so moving forward, fusion energy power plant designs utilize superconductors as the main way of creating their magnetic bottles. And I'll come back to this point, but superconductivity in these very special materials occurs below critical temperatures, critical magnetic field, and critical current density. And one of the things that's a challenge with superconductors is that critical temperature is very cold, usually in the tens of Kelvin. And so that is one of the challenges to using these materials. So going back to this plot, there is a particular super type of conductor that has been in existence for many decades and makes a really applicable superconductor for making magnets. And however, it only could operate up to about 6 Tesla and still remain superconducting. So using that technology, sort of the advanced technology of superconductors, an experiment is being built in the south of France called ITER. It is an engineering marvel. It is incredibly exciting for the development of fusion. And it is pushing the limits of the superconductor to create something near the conditions you would need for a reactor. So these Qs are getting close to what would be applicable for a power plant. And showing here some pictures from ITER. It's under construction. This is a facility being built. On this picture here is a picture of a segment of the donut, and the people are there for size scale. So this is a very large device, and again, is one of the things that makes it an engineering marvel to design something at that scale, incredibly tight tolerances. And this is a project being pursued, is an international collaboration. The United States is part of it. And you can see some of the flags there. And this is a wonderful history of fusion. Fusion has always brought the world together. It has always been an international project that scientists, engineers have come together, politicians, for the betterment of society. And so the United States is a proud partner in this. And again, ITER is a device that would achieve a Q of around 10, producing about 500 megawatts of fusion power. And in one pulse, that is up to 200 gigajoules of fusion energy. And just to kind of review where JET demonstrated about a year ago, we were breaking records at around 50 megajoules of fusion energy. So this is a big leap in the development of fusion energy. So ITER is big, and it's big for many reasons. Again, very valuable to develop fusion energy. But one key issue is, as we move forward, ITER is too big for a power plant. So one of the technologies that's opening up avenues for more compact power plants is the development of high temperature superconductors. These materials have existed for many decades. They were first discovered in the late 1980s. And again, reviewing that superconductivity depends on critical temperature, current density, and magnetic field strength. And so that's shown on this plot with different axes, where the gray surface describes what are known as low temperature superconducting materials. And these are the type of materials being used in the magnets for ITER. High temperature superconductors expand the range at which the materials stay superconducting to higher temperature, to higher magnetic field, and to larger current density. And this technology opens up the possibility of making stronger magnets for fusion application. The challenge, though, was that the materials that were HTS, or high temperature superconductors, weren't really well suited to be used in a magnet that would be under a lot of stress and strain in a fusion reactor, fusion power plant. So the next breakthrough was that how to use this high temperature superconducting material, which is kind of brittle, in a package that could be used to make a magnet out of. That became available in 2009. So it's called HTS tape. There's a cross section down here showing some of the sandwich layers that go into this. And it's not only how it exists, but how you make it at very kilometer type lengths so that you could turn that eventually into a magnet. And this picture here is showing some of the tape on reels, and it's, you know, very thin type tape, almost like what you would see in a cassette tape, for those of you who remember the 80s like I do. So born of this idea that HTS tape could be turned into magnets, a few years ago, the concept of a reactor called ARC was developed and published that takes advantage of the high temperature superconductors. And you can see the gray area now has opened up. It's like drawing back a curtain. Now you are able to produce power plants that can access the Qs needed for a power plant at the size scale similar to existing tokamaks like JET. So this is now a comparison in scale to ARC, which is an acronym for affordable, robust, compact. And if you are a fan of Iron Man, yes, it is completely taken from the arc reactor in Iron Man, and ITER to scale. And some of the parameters there comparing the size. So again, arc being a more compact, smaller device, the magnet technology, arc using HTS magnets, ITER using low temperature superconducting magnets, the field strength. And again, the arc is able to get to higher magnetic field, the fusion power output, the Q is achievable. And then the goal, ARC is a power plant. It would put electricity on the grid, where ITER does not have a blanket. It is a science experiment. It is not built with the purpose of being a power plant. So now the final part of the talk is the fastest and surest way to a fusion energy power plant. Commonwealth Fusion Systems, who I joined about a year ago after my time at PPPL, was founded in 2018 to build the first ARC in the 2030s. And so what needed to happen to make that goal is going from known science and engineering on existing tokamaks. And this picture here is of a tokamak that was at MIT called Elkotor CMOD, and be able to make the transition to building tokamaks out of HTS magnets and building a fusion power plant. So the first part of the roadmap to doing that was to demonstrate the world's first large bore HTS magnet on the scale that you would need for a fusion power plant. So in 2000, it gets a little covered by the Zoom thing. I think it's 2021. Yeah, there we go. Thanks. 2021. CFS and MIT in a joint demonstration were able to build, construct, test a large bore 20 Tesla HTS magnet and demonstrate that this magnet could be made and operated at the fields needed for a power plant. And so this was a big breakthrough because, again, this now pulled back the curtain in that space of the tokamak size and magnetic field strength and allows much more compact power plants to exist. Thanks. So the next step on the road, filling in the timeline between where we were with the existing tokamaks and the construction of ARC, is a demonstration called SPARC. And SPARC would integrate the high temperature superconducting magnets in a tokamak system with the fusion that would be happening inside the plasma. So SPARC is a compact, high-field deuterium-tritium tokamak. It will achieve Q greater than 1 in 2025 and Q of 11 before 2030. The maximum projected parameters is that it would produce 140 megawatts of fusion power. It would run for pulses of 10 seconds. So that's 1.4 gigajoules of fusion energy produced with each pulse. SPARC, like ITER, is not a power plant. It would have no blanket. And with the demonstration of the HTS magnet, Commonwealth Fusion Systems secured $1.8 billion in Series B funding to support the construction of SPARC, its operation, and the research and development needed to have ARCs constructed within the next decade. So this is a bit of a science-y slide, but I really enjoy talking about it because one of the key cornerstones of SPARC is that it's built on the database of publicly funded research that has occurred in fusion up until this point. So all of these black dots are data produced at a tokamak facility somewhere around the world and contributed to our international database. And on each of these plots are dimensionless quantities. And if you are building a big new jet, you don't just say, well, we'll build it and see how it flies. The first thing you do is you make a model of it and you put it in a wind tunnel and you calculate a lot of quantities that are dimensionless, ratios of things, size to speed, things like that well, actually end up being dimensionless. But then you use what you learn in the wind tunnel to then qualify what you're going to build in the final product. And so that's why it's very often we rescale what we learn in science in these quantities as we project towards the next step. And the point being here that SPARC, which is shown on these plots in the red triangles, overlaps many pulses on the experiment jet that achieve many of the similar properties. And so as we are looking towards the operation of SPARC, we have a lot of confidence in the ability to produce the target conditions that we need in the plasma for the demonstration. So this is a bit of a summary slide on, again, this plot that sort of summarizes the importance of going to high field tokamaks, again, showing where ITER will sit and where the future would go if we were restricted to the low temperature superconducting magnets. And in the high temperature regime, building on some results from CMOD, which was used copper magnets to develop the high temperature superconducting demonstrations in SPARC and ARC. And again, all of these devices shown at scale on this slide. So I traveled back to New Jersey. It's good to be back in the area. My family, we spent 7 years here, so it was very welcome homecoming to come back. And we were coming from Devens, Massachusetts. So this is where the Commonwealth Fusion Systems headquarters is located. To give you a sense of the site, the office building is now open. So is the cafeteria. The Lawson cafeteria is now open. And connected to it is the magnet factory. So this space is where the technology needed to develop these magnets on a factory floor is coming to fruition so that you can produce the magnets at the speed needed to support not only SPARC, but then the first ARC reactor, first ARC power plants. The building here is the SPARC facility, where SPARC will sit in the middle of that facility, and then there are buildings off to the side supporting the different aspects of the tokamak that are needed. And just this month, we had a grand ribbon cutting, and it never fails to amaze me how politicians show up to hold goofy scissors and cut ribbons, but they came. So in here in this picture is Bob Mumgard, founder and CEO of Commonwealth Fusion Systems, one of the founders. Standing among a cadre of politicians, including the Secretary of Energy. And reason I wanted to show this picture is the emergence of the private sector in conjunction with the public sector is, the public-private partnership is pushing the acceleration of fusion development faster. But if you have a great idea, many follow, and that's exciting. It's really exciting because we're building up a new industry around fusion, and in particular around high temperature superconducting magnets. So probably the company with the most aligned goals to CFS is Tokamak Energy. So this is a company that exists in the UK, and they are also constructing high temperature superconducting magnets and testing them in tokamak designs. The UK government is also have a program to develop a reactor and put it on the grid using high temperature superconducting magnets as one of the key components. And there are a number of US and also international companies that are either coming online or have existed for a little bit who utilize high temperature superconductor as the key technology to unlocking compact fusion reactors. So hopefully in these slides was able to walk through the high temperature, the high field approach and how it is the fastest and surest way to a fusion energy power plant. And I just wanted to say one slide on and why it matters. With climate change, it usually is not something that it's, singing to the choir. People understand the challenge that the world has ahead of it. But often it's wondered, how does fusion fit into the solution? We need a solution. Where does it fit? Well, the rapid decarbonization of the world's energy economy requires new firm energy sources. And it's going to need a broad mix of solutions. So obviously we are very familiar with solar and wind, and we need to ramp those up as fast as possible. But we also need firm energy sources. And I showed a plot here from the Department of Energy. They have a group of scientists who work on projections, combining both policy and economics to project forward the US annual electricity production going up to 2050. Projections are not destiny, but it gives a sense of the problem at hand, that it's hard to displace firm energy sources such as natural gas and coal. And these are power sources that are available where you need it and when you need it. And so one of the real strengths of compact fusion power plants is they can fit in the footprint of existing gas and coal power plants. So this allows very rapid market penetration. You don't have to build new interconnects. You don't have to buy new land. And when you're bringing in a compact fusion power plant, it's good for the community. No longer are you, worried about the air quality from burning fossil fuels. And if you compare it to fission power plants, which exist now, the community also doesn't have to have the concern of long-lived radioactive waste on site. So I want to just thank every one of you for attending today. And also I know I'm going to have a very vibrant Q&A, and I look forward to that. So I just want to thank you for letting me share my passion. I touched on my, inspiration from the NASA program when I was young. What I'm showing here is a picture of Gene Kranz at NASA. So if you've watched the movie Apollo 13, he wears the white vest. And was instrumental in Apollo 13 and the Apollo program. I get to live my Gene Kranz dream on a day-to-day basis. So when I was at PPPL, I spent a lot of time in the NSTXU control room as a physics operator, which is kind of a weird title, but it is analogous to a flight director. And now in my new role at Commonwealth Fusion Systems as head of physics operations, we're building up the control room that will run SPARC and in the future, ARC power plants. And so also sort of analogous to the space program, NASA was a publicly funded program, incredibly successful, and developed a depth of knowledge. And the new way of working is NASA now partners with many private industry partners to commercialize low Earth orbit and beyond. And so similarly, fusion is going through a similar transition of a depth of public funding programs giving birth to a new industry in a public-private partnership. And I'm excited that I've been a part of both of that in my career. So thanks again.
Okay, so microphones are on the way, and we'll pass right there, Didi, and I'll come around. And Harry, yeah, if you can put the Zoom participants back up on the screen.
You mentioned very briefly Series B funding. What is that? And are companies such as PSE&G spending any of their money on this type of research?
Yeah, thanks for your question. Harry, I don't know if I can go to my backup slides, but Series B is a term used in venture capitalism. So when a startup company is raising money with a good idea, first they raise Series A money, which is viewed as seed money, and then they raise Series B money, which is really where you put your product. Thanks. So thanks, Harry. So just to show here, so this is I can give you a sense of the private investors who are investing in Commonwealth Fusion System. There's a broader list of investors who are investing in private fusion companies around the world. But I know CFS is very proud that the investors who are have put their money into CFS are long-term committed investors because they want to see solutions for climate change. So PSE&G is not investing in this, but they would be a potential client for the first fusion power plants.
So my question has to do with why does it have to be a high field tokamak? Meaning you can have high field like Stellarator, high field, one that the two few the other one where they get knocked against each other. I don't know what that's called.
Yeah. It doesn't have to, it can be all. We want fusion to commit to be a part of we need fusion to be a part of the solution for climate change. And so we need all great ideas pushing forward. The title is that we believe that high field is the fastest and surest way to deliver that. I am a firm believer that if humanity will look back and laugh at our use of fossil fuels and laugh at what our first fusion power plants look like, right? They will look so sort of grotesquely underdeveloped. So we don't know what fusion power looks like way in the future, but we do know if we need it on the grid now, high field tokamaks offer the fastest and surest path to get there.
I'd like to get back to the Q that you mentioned. And I like to think of Q being in a circle. And I was wondering if the power to keep the superconducting magnets cold is inside or outside of the Q circle.
That's
for
right.
Input and output considerations.
That's right. So it's very important to draw that boundary around the plasma and to consider the energy going into the plasma, and the energy coming out is what defines Q. And anything to do with the efficiencies of a power plant, including energy needed to create the cryogenically cold temperatures for the magnet, is not part of a definition of Q.
I kind of thought that. Thank you. One more quick question. The neutrons coming off will impinge inevitably on the walls of the tokamak, and they can be destructive to the metal, etc. What is your thought on that problem?
Well, this is where the investments that are being made in the public sector have been so valuable. There are a lot of there's a lot of ongoing research on the material properties and how they change under that type of interaction with neutrons. And so that's research that's ongoing and is the next frontier of what we're working on towards reactors. We'll learn power plants, we'll learn things as we build the first of these kinds. But they're solvable problems. They just take a certain level of research and development.
Hi, so I have two questions. One is, one of the first slides you shared with us was where the neutrons, you had 5, 3, and 2, and then they converted into a 4 and a 1. Now the 1 neutron seemed to have much more energy than the one that had the 4 neutrons. But the way I've understood the presentation is that you're using the one with the lower energy source to build the tokamak. So when I looked at the slide initially, I said, oh, they're going to use the one with the higher energy source to start building out the energy, the power plant. So I wanted to understand that. If, first of all, whether did I understand the presentation right? And then did I, what was the thinking behind that? The second is, I live around 3 miles away from this radius. And I'm thinking, what is the safety protocol that needs to be put in place to manage something like this that has such a high energy source and has so much of dependency on the magnetic fields to contain it?
Great question. So very astute in noticing that in the fusion reaction of deuterium and tritium, that the byproduct, helium and the neutron have different energies. If you wrote those numbers down and wrote them as fractions, 80% of the energy goes to the lightest thing, the neutron. 20% of the energy goes to the heavier thing, the helium. And in that picture of what a power plant would look like, the energy that is in the helium atom, that lower amount of energy, would stay in the plasma and help keep the plasma at the temperatures you need for fusion. And that energy from the neutron would come out and into your blanket and be something that you would harness as your energy source. So yes, so hopefully that answers your question. Yes, the energy division between the two, but all of that energy is captured in a sense that some of it stays in the system and eventually leaks out through light and other ways that the plasma would release its energy, and some of it through the neutron. Now, the safety aspect of it, that is where fusion shines. It is the plasma is very well, it's very hot, but at the same time, it wants to get cold very fast. If you remove energy from it, let it touch the cold walls, it kind of just goes away. And this is one of the challenges of actually, that we've had to address and higher magnetic fields has helped sort of keep that plasma at the higher temperatures. So it is an energy source that, I would be happy to put my family right next to. It is inherently safe.
Just before the question there, it fits right in what you said. People are asking about how do you go from heat to electricity?
Yeah. Yeah, the question is, how do you go from heat to electricity? And it would look like a power plant today, where we are using energy to heat water, turn it into steam, and turn a turbine. And that, again, is why compact fusion reactors that could fit into the footprint of existing gas and coal-fired power plants would be very resonant, because you could take advantage of that infrastructure that exists.
Hi, you just kind of touched on what my question was going to be. Steam plants are fairly inefficient, so getting exergy from a fusion reactor seems like the most difficult problem, and the one I don't see addressed very often is how you've got these very, very fast neutrons. I assume that's where all the energy is located mostly, and how do you, hurting neutrons is like hurting cats on amphetamines. I mean, it's like, how do you focus them, and how do you get them to steam or even a Brayton cycle
Sure.
power plant?
Yeah, so we have our magnetic bottle, the tokamak, and around it is a blanket. Harry, I don't know if I can go to a slide of ARC, but ARC, the slide that was up there showed, I didn't point it out, but maybe a couple more back things, Harry. No, that one will be good. We'll just use this one. There is around ARC a liquid blanket, and that blanket is of sufficient thickness that the neutrons would be absorbed in that blanket. So all the energy in the neutrons would end up heating that material. This is a liquid immersion blanket, and then that heat would be captured in your heat exchanger to boil water, turn it to steam, turn a turbine. So hopefully that answers your question of the blanket is what's there to absorb the energy from the neutrons.
Do lasers play any role at all in the HTS tokamak design?
They don't. No, they are a different concept.
Awesome, thank you. I was wondering about in the tokamaks, the possibility of turbulence or instabilities and what that's based off of, whether it's the property of the plasma or size of the tokamak or the magnetic field itself.
Yeah, that's a great question. And I'm trying to think of we love to talk about turbulence because it's kind of the scientific frontier, but I want to keep it at the right level here. When we put energy into the plasma, eventually you're in the hot core, that energy will move its way towards the colder parts. And the energy that is moving across the magnetic field line, a lot of times that is driven by very, very small turbulence in that plasma. So understanding that turbulence is something that is important for when we're designing the heart of our power plants, how the plasma would hold on to the energy. And in terms of instabilities, there are instabilities that can happen in the plasma when you drive them to the limits, just like a NASCAR race car. Like you can keep it on the track as long as you know how to slow down for each turn, but sometimes you want to, in science, see what happens if you go around that turn really fast. And so a lot of times in tokamak research, we study those instabilities. How does it act when we take it to its limit? But in a power plant, we would stay far away from those boundaries. So we do study turbulence and instabilities in tokamaks, and it's part of our designs, but plays less of a role, I guess you could say, and once the tokamak is operating this power plant.
Hi, Devon. I think you may have. Okay. All right, let's try that again. Can you describe in a little more detail your plans for the first wall on SPARC?
Sure. So SPARC uses tungsten. Tungsten is a material that has a very high melting temperature. Happy to talk more details. It's a very technical question, but that is the material that's being used on the first wall, the wall that would see the plasma that's being levitated inside of the tokamak.
I think you may have answered my question with the description of instabilities, but besides superconductivity, what do you see as the next biggest technical challenge to getting to where you want to be with Q?
Sure. Well, with Q, that's the plasma physics. We're in pretty good shape with that. We've got a lot of basis for that. I think the next challenge is everything that goes around it to turn it into an energy source. And that's where a lot of the R&D is right now. Someone had a great question on materials. So as an engineer and you're designing materials, you need to know certain coefficients and what they might be in a very unique situation. So research into that. And then the blanket technology. So we have yet to really fully demonstrate in our fusion community a fully integrated blanket system with our system. So I think any fusion concept that uses deuterium and tritium, that's sort of the next frontier of demonstration.
On the tape that you, I'm sorry, the photo you showed of the tape, is that being used in the system you're building? Or is that just a technology that has been designed that's used in another facility?
That's a great question. Yes, so the tape is a component in the magnets that are being built right now for the SPARC device and would be used in the first ARC power plants.
So now that the product is, these tokamak products are attracting a lot of private money, those investors are going to expect a return. Is there any plans for them to share any patents or intellectual property or the results of their experiments with the various other products that are in the space?
That's a great question. One of the things that I really enjoy about the environment of Commonwealth Fusion System is openness and transparency. The physics basis has been published in peer review journals. We continue to publish and really view what we learn from a plasma physics standpoint is for the international community, just as research has been in the past on this. Where the intellectual property lies is in the technology, the magnets, the blanket technology, and how you manufacture those at scale at low cost. And so that's what the investors are looking for a return on in our particular company. But I think going forward in fusion industry, it's that technology that becomes the product.
You mentioned pulsing, and I know NIF is operating on a pulsing basis. Do you expect that a power plant would operate with pulsed waves of energy, or would it be in a steady state of some sort?
That's great. Great
I
question.
know that's far in advance, but
it's not too far in advance. So the demonstration at Livermore did use lasers, very short pulses, nanosecond pulses. And in order for a power plant concept would have to do that repeatedly. Traditionally, tokamaks are pulsed. I mentioned SPARC would run for about 10 seconds. ITER would run for a couple minutes, but still would make their plasma pulse, and then it would stop and you'd have to restart it. There are different ways of approaching a power plant. We think that the high field approach lends itself well to a pulsed design where the tokamak would pulse for a few minutes and take a few minutes off and then pulse again. And with the blanket is a kind of a reservoir of heat. So it sort of evens out that sort of up and down. And it also makes it very convenient for power on demand. The energy operator says, I need power. Well, now is the time. You can bring it up. You know, when solar and wind die down for the rest of the evening, you can bring it up and start doing that pulse sequence. So the system would be kind of naturally set up for on-off type of operation.
Thank you for the talk. It was very enlightening. The question I had, a lot of complaints you always hear about, say, electric vehicles and home batteries is the materials used in those and how they're sourced and how energy intensive they are. And I couldn't help but notice between, the tungsten, the lithium, and all the other materials surrounding the ARC, and looking at the size of ITER, what are some of the sources of the supply chains for these materials? What are some thoughts or the status of the ethics of it, and how much energy is needed going into the equations, not just inside of Q, but outside of Q?
No, it's a great question. I mean, to say a couple points on that. One, the supply chain, building up the supply chain for fusion industry is happening right now. And that has been really exciting to see that companies that are interacting with CFS and other private companies are not just building one product, they're building a whole concept of how they would provide that product for the next decades, because they recognize fusion coming onto the grid. And so building up that supply chain is part of what CFS and other private companies are doing. ITER, for example, is pretty much doubling the world supply of low temperature superconducting material just to be able to make those magnets. When the demonstration coil occurred at MIT of the high temperature superconductor, that accounted for about 10% of the world's supply of HTS tape. In the convening years, HTS tape manufacturing, based on CFS's success, has grown. I don't know the exact number, but I'm going to say of the order of like 100-fold. It's rapidly now. You're putting out high quality HTS tape at a very rapid pace. Now, the ethical aspect and that's a great question, and I know that it's something that's very important to the ethos of CFS, but I wish I could have a more detailed example. But new technology does demand new novel materials, but lithium is something, the amount of material needed, at least for the fuel, is little. And then for these actual systems, a lot of money is spent on concrete whenever you build something. So, I think a lot of concrete goes into these designs. So thank you for that question.
What happens during pulses, and are longer or shorter ones more efficient?
That's a great question. Yeah. So during a pulse, you actually start with a cold gas. You have to put energy into that gas to turn it into a plasma and get the temperature up to fusion. Once the fusion starts to happen, it actually starts to heat itself. You can dial back your heat. So there's kind of a little bit of a spark plug, you could say, something to kind of get that fusion reaction going. And then so during the pulse at its highest temperature, and you're holding on to it for minutes, that's when you're collecting energy from that process. And then you have to cool everything back down, the plasma back down, and start it back up again in a pulse. When it comes to the efficiency, this is something that is looked at when designing power plant concepts. And there is lost efficiency by the start-stop, but it tends to simplify the technology that we need. And so the cost benefit of pulsing is a lower cost facility to build. So excellent question. Thank you.
How do you heat the fuel up to like the fusion temperature?
That's a great question. There's lots of approaches. SPARC and ARC use microwaves. So beep, boop, boop, heat plasma. But beep, boop, boop in your kitchen is 1 watt ish, couple, watt or so. The RF, the radio frequency heating on SPARC is megawatts of energy. So thousands of times the power of your microwave. But those microwaves are launched into the plasma and are absorbed by the plasma because it has charged particles, and that raises the temperature of the plasma to the fusion conditions.
Got a question from Zoom. that no one's asked yet, which is what role, if any, does artificial intelligence or machine learning play in your research?
I am actually not a person. I'm just Chat GPT. So, right. So obviously the new frontier is being adopted in all technology development, and fusion is not, we're trying to utilize it as best we can. So where does it come into play? Well, I'll talk to something that's what I work on a daily basis, and that is how do you control with what we call our actuators, so the magnetic fields and the RF, how do you meet the conditions that you're looking for inside of the plasma? And you do that through models that can run at the same time you're running your plasma. These models are running in conjunction, and you're forecasting. How am I doing? Am I doing all right? Is everything good? Where am I going? And those models have to run fast. And so you tend to run them with approximations so that they run quickly. With artificial intelligence, we can look over databases of lots of tokamaks. We can look over databases of lots of simulations that took a lot of time and boil them down to an algorithm, a calculation that can run really fast. And so that's one application of artificial intelligence.
Thank you. There's someone in the back. Yep.
So I was wondering about maybe applications of this tokamak and fusion research to other areas of science. Maybe I know that like in the sun, for fusion to occur, you need quantum tunneling and that little bit of extra bit of energy. And there's like the proton-proton change, which spits out like a neutrino, or like you could just think about like accretion disks around black holes or supernovae. I was just wondering if this kind of fusion research could be applied towards other areas of science.
It happens every day here at this lab. So this is a lab that was founded by Lyman Spitzer, a professor at Princeton, directed at making a commercial energy source or making a power source out of fusion energy. And now the lab supports research across a broad spectrum of silicon chip development that uses plasmas, to understanding solar storms so that we can protect our satellites and astronauts eventually who are in low Earth orbit. So, and then the technology that gets developed for fusion in terms of RF heating and other parts of materials all tend to spin out into different parts of technology and science development. So I hope that gives you a sense that anytime we push on the frontiers of science and technology, it does have positive impacts on a lot of different areas.
Thank you.
So time for a couple more questions right off of Zoom. Oh, there we go. I'll do one from Zoom. We'll get you a microphone. Thank you. Can you please comment on the cost per unit energy generated with the current state of fusion generators in comparison to other commercial forms? Will fusion be economic?
Right. Yeah. Thank you for boiling it down, because I don't know if I could give a quantitative number because it's a little bit out of my expertise level, but that the reason private investors are excited about fusion is because they run those numbers and they are familiar with what it takes to break into an energy market. And the energy market is hundreds of trillions of dollars. I mean, there's a lot of money spent in energy, and not just the energy that we need today, but what our energy demands are going to be in the future. And that investment is recognizing that even if you can capture a small segment of that for the applications where fusion is the best solution, it is going to be cost competitive.
There we go.
Climate change is with us now. And you mentioned that these the fusion facilities would be ready in 2030. And I'm wondering, is there any other form of competition other than wind and solar? Competition is a great way to make things happen sooner. And we definitely need something sooner when I think about what's happening in California. I'm wondering, do you have competition in in using fusion as the newest source of energy? And if so, are you likely to succeed?
Well, thank you. Yeah. So just one thing I always want to point out is wind and solar are not competitors. They fill a very particular need and they're ready right now. I did bring up that wind and solar will work very well, but not in all applications. And some of the missing applications are firm energy sources. So things that can be close to urban centers, that can take advantage of existing transmission lines and land use, and that can be turned on and turned off to fill in the gaps when the wind and solar might not be available. And so fusion is one of the solutions for that need. And so there's no necessary competition. We simply are just racing against time. Yes.
Yeah. So you mentioned to use the model to control your magnetic field. So last year there's a research between DeepMind and I think Swiss lab to use deep reinforcement learning to control the field. Do you think that can play a role and increase your Q more efficiently?
No, absolutely. That's really kind of getting to more detailed example of what I meant as far as DeepMind being a company that collaborated with a public institution in Switzerland to demonstrate artificial intelligence learning from their models how to control the actuators, which are the magnetic field. And that is, again, the application that we are using as part of our system of being able to control the plasma. Now, does it increase the Q? Maybe not, but it does provide us an accelerated path to getting answers that we need in SPARC, and could also help us develop simpler products for ARC.
So I think our last question is an interesting one right from Zoom, which is, how do individuals support the development of fusion energy?
Well, maybe that's a question for Andrew.
Wait, hold on. It says Devon. How do individuals support development of fusion energy?
Sure. Well, yeah. So certainly, I was a tour guide for PPPL, and encouraging people in society just to know more, to ask questions, to attend science on Saturday. If you are moved that you want to be actionable, certainly we need support in any new energy source from the government. That could be in defining how it will be regulated, in defining how the government will use tax breaks to incentivize the development of a new industry. So, and then the politicians also fund public research, which accelerates our discovery in fusion energy as well. So that is another actionable way for people to bother wonderful politicians on the policy surrounding fusion energy.
Thank you. Thank you for that. And I think with that, we could give another round of applause for just a wonderful lecture.